Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of BITSAT question papers, we're going to be answering previous year questions of physics asked in BITSAT 2018. So this is the second video of this section, so we're going to answer some other questions of physics asked in BITSAT 2018. These questions are very important and I'm sure that it will be helpful for all of you watching. So if you want to access our previous video, don't forget to click the link of the playlist in the description box down below. More about it at the end. So here comes our first question. A block of mass 2 kg is placed on a plank of mass capital M equals 10 kg, which is placed on a smooth horizontal plane. The coefficient of friction between the block and the plank is mu equals 1/3. If a horizontal force F is applied on the plank, then find the maximum value of F for which the block and the plank move together. You can take acceleration of gravity as 10 meters per second squared. So which of these options are correct? So we have the diagram of the given question here. So we have a plank, then we have a block sitting on it, and it has a height h and a width h/4. The coefficient of friction between the block and the plank is given as 1/3, and there's a force F acting on the plank. So in this question, what we essentially need to find out is we need to find out the maximum value of F for which the block and the plank move together. Now, for the block and the plank to move together, the relative motion between the block and the plank must be 0. So this means that no slipping takes place while the plank is pulled. So in order for no slipping to take place, both blocks have to move together, and their acceleration will also be the same. Now, how do you ensure that no slipping takes place? For no slipping between M and M, the force applied on the plank, that is F, must be greater than or equal to, must be less than or equal to mu times the weight of the block. Mu times the total weight. So in this case, F is less than or equal to mu times M plus M into G, where capital M stands for weight of the block, weight of the plank, and small m stands for weight of the block. So the maximum force can be calculated as mu, that is 1/3, times M plus M gives you 10 plus 2, and then G is also 10. So 10 plus 2 is 12, so 12/3 into 10. So 12/3 gives you 4. 4 times 10 is equal to 40 Newton. So 40 Newton is the maximum force that can be applied on the plank to make sure that both the block and the plank move without slipping. So if you were to look at our following options, you can see that option B, 40 Newton, is the correct option for this question, which is asked in 2018. Let's look at the next question. The susceptibility of a magnetic substance at 300 degrees Kelvin is 1.2 into 10 raised to minus 5. The temperature at which the susceptibility increases to 1.8 into 10 raised to minus 5 is. So here the question is asking us to relate the magnetic susceptibility of a substance to the temperature of the same substance. So for that we use Curie's law. So according to Curie's law, susceptibility is equal to C, that is number of moles, divided by T plus theta. So from this relation, you can find out that magnetic susceptibility is inversely proportional to the temperature. So x1 by x2 gives you T2 divided by T1. So this is the current relation between the susceptibility of the magnetic substance at two different temperatures and the two different temperatures themselves. So Now we'll apply the values. The first susceptibility value given is 1.2 into 10 raised to minus 5. And the susceptibility at the second temperature is 1.8 into 10 raised to minus 5. The second temperature is unknown, but the first temperature is given as 300 degrees Kelvin. So over here you can cancel 10 raised to minus 5, so you get, and you can multiply 10 on both sides, so you get 12 by 18 equals T2 by 300 degrees Kelvin. 12 and 18 are multiples of 6. 12 goes into 6 goes into 12 two times. 6 goes into 18 three times. So 2 by 3 equals T2 divided by 300 degrees Kelvin. So over here you can get T2 equals 300 degrees Kelvin times 2 divided by 3. So 3 goes into 300 100 times. So 100 Kelvin and 2 gives you 200 degrees Kelvin. So the temperature at which the magnetic susceptibility is 1.8 into 10 raised to minus 5 is 200 degrees Kelvin. So if you were to look at our options, you can see that option B, 200 degrees Kelvin, is the correct option. So in this question, the important thing is to use Curie's law. So Curie's law states that x equals c divided by t plus theta, and then take the relation between x and t and solve it with simple algebra. So that concludes this question. The next question is, magnetic moment of a bar magnet is, say, m. The work done to turn the magnet by 90 degrees of the magnet in direction of the magnetic field B will be. Is it 0? Is it half MB? Is it 2 MB? Or is it MB itself? So how do we solve this question? So over here, we can equate the work done by the magnetic moment as equal to its potential energy. And the potential energy is represented as minus MB cos theta. So if you have two values of theta, then that will be MB times cos theta 1 minus cos theta 2. Final, initial. So the work done here at initially the bar magnet is oriented, say, at 0 degrees, and then the work done is to turn the magnet to 90 degrees. So therefore, we don't know the value of m, we don't know the value of b, so we can just write that. Cos of theta 1 is cos 0, cos of theta 2 is cos 90. So it's MB times cos 0 is 1 minus cos 90 is 0. So the work done by the bar magnet to turn 90 degrees in the direction of a magnetic field B is m times b, where m is the magnetic moment of the bar magnet. So among the four options, the correct option is option B. So here we use the formula for potential energy. Potential energy is minus MB cos theta. So it's basically minus MB times cos theta 2 minus cos theta 1. But then we took the minus inside, so it becomes MB times cos theta 1 minus cos theta 2. So from this formula, we applied the values of theta. First, it's at 0, and then it's perpendicular, so it's at 90. And then finally, we got the answer. Work done is equal to m times b. Magnetic moment times the magnetic field B. Let's look at this question. If m is the magnetic moment and b is the magnetic field of an object, then find the torque. Now, the torque of the magnetic field is expressed when there is a coupling force acting on the magnet. So the magnetic moment is acting one way and the magnetic field is acting another way. So therefore, it is always represented as MB sine theta. So if a product has sine theta, then this is its cross product. So therefore, the torque expressed by this object is given as m cross b. So So over here, the important thing to note is that the magnitude of torque is mb sine theta, because the coupling force is acting, and then it's based in, and then it's going perpendicular. So the angle created with the magnetic field forces it to act perpendicularly in, has a perpendicular component, and so therefore the torque's magnitude is mb sine theta. Sine theta is coming in a product of two vectors when the product is a cross product, so therefore the torque is m cross b. So therefore option C is the correct option to this question. So all the other products are incorrect, because for D and B there is no sine theta that comes into play, and option A is the dot product, which means it has to be in terms of cos theta. So that is also incorrect. Correct option is m cross b for the expression of torque. Next question. A copper rod of length L rotates about its end with an angular velocity omega in a uniform magnetic field B. The EMF developed between the ends of the rod if the field is normal to the plane of motion, plane of rotation is. So how do we solve this question? Well, over here, the copper rod rotates about one of its ends, and it completes one revolution in a time that we can consider as capital T. So therefore, when it's rotating, it obviously experiences a change in flux, magnetic flux. So delta phi equals B dot A, and over here, since it's rotating about one end, the area will be pi r square, which is pi times the length of the rod, that is L squared. And according to Faraday's law, induced EMF is equal to delta phi divided by time period. So therefore the EMF E is equal to B times pi L squared divided by T. So 1 by T can be taken as the frequency, the linear frequency F. Now, since the angular frequency omega is represented as 2 pi F, we can write F as omega divided by 2 pi. So therefore, the EMF is equal to B times pi L squared times omega divided by 2 pi. So the pi gets cancelled here. So you have 1 by 2 B omega L squared. So this is the correct expression for the induced EMF in this question. So the EMF developed between the ends of the rod of the field is normal to the plane of rotation is option B, half B omega L squared. So that is the correct answer to this question. Let's look at the next question. Consider the elastic collision of a particle of mass m moving with a velocity u with another particle of the same mass which is at rest. So after the collision, the projectile and the struck particle move in directions making angles θ1 and θ2 respectively with the initial direction of motion. So you need to find out the sum of the angles θ1 and θ2. So we have a particle of mass m, and it's moving with a velocity u1. And then we have another particle here that is also of mass m. Let's represent them as m1 and m2 respectively. And here the value of the initial velocity is 0. So this particle hits the other particle, and then they move off in an oblique collision. So this is an example of oblique collision. So in this oblique collision, one of the particles moves at an angle θ1 with the straight line, another particle moves with an angle θ2. Both of them have velocities v1 and v2. So therefore, you would have particles, I mean, you would have the component of the velocity along the x-axis and also along the y-axis. So more on that when we solve this question. So let's start solving it. So this is a standard case of oblique collision. Now let's apply the conservation of momentum in mutually perpendicular directions. So that means we're going to apply conservation of momentum for both the horizontal components as well as the vertical components. So along the horizontal component, we had m1 moving with the velocity u1 and m2 was moving with the velocity 0. So the left-hand side will be m1 times u1, and the right-hand side would contain the, horizontal component of both these velocities. So that means m1 v1 cos theta 1 and m2 v2 cos theta 2. m1 v1 cos theta 1 plus m2 v2 cos theta 2. So since m1 is equal to m2, you can cancel out both. You can cancel out the mass from this equation. So m1 equals m2 equals m. You will get the first relation u1 as equal to v1 cos theta 1 plus v2 cos theta 2. So let's take this as our equation 1. Now, if we take along the y-axis, you notice that earlier the mass was moving only along the horizontal component, so the vertical component was 0 for both particles. So therefore, the left-hand side has to be 0. So the right-hand side here has v1 sine theta 1 and v2 sine theta 2 for both masses. So now it'll be m1 times v1 sine theta 1 minus m2 times v2 sine theta 2 because they are moving in opposite directions. You can remove the mass here because then you can take the mass common out and then take it to the left hand side, so that will be 0. So therefore 0 is equal to v1 sine theta 1 minus v2 sine theta 2. Now the reason why it's minus because they are in opposite directions in the y-axis. Now we consider this collision as elastic. So for elastic collision, we conserve the kinetic energy. So therefore, when we are conserving kinetic energy, we'll write kinetic energy in the first case, that is half mu1 square equals half mv1 squared plus half mv2 squared. So the kinetic energy of the first particle is distributed equally among both the particles after oblique collision. So since half and m are common, we can write u1 squared as equal to v1 squared plus v2 squared. So the equation along the y-axis is equation 2, and the equation that we just got, we can consider that as equation 3. So now what we're going to do is we're going to square and add equations 1 and 2. So on the left hand side you would have u1 squared plus 0 squared, so u1 squared is equal to, on the right hand side you would have v1 cos theta 1 plus v2 cos theta 2 the whole squared plus v1 sine theta 1 minus v2 sine theta 2 the whole squared. We can write that down as v1 squared cos theta 1 cos squared theta 1 plus v2 squared cos squared theta 2 plus v1 squared sine squared theta 1 plus v2 squared sine squared theta 2 plus 2 times v1 v2 cos theta 1 cos theta 2 minus 2v1 v2 sine theta 1 sine theta 2. So over here we can take v1 squared common. You would get cos square theta 1 plus sine square theta 1 plus v2 squared as common, so you'll get cos squared theta 2 plus sine squared theta 2. Now both of these brackets will be equal to 1 because sine squared theta plus cos squared theta is equal to 1. Now we take 2v1 v2 common. So 2v1 v2 is common, so you get cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. So this is of the form cos A cos B minus sine A sine B. So that will be equal to cos A plus B. So v1 squared plus v2 squared plus 2v1 v2 cos of theta 1 plus theta 2 is the right hand side, and on the left hand side it's u1 squared. Now using equation 3, what we are going to get, so what we're going to do is we're using equation 3 and applying in equation 4. We get u1 squared equals u1 squared plus 2v1 v2 cos theta 1 plus theta 2. So u1 squared goes to the left hand side, so the left hand side now becomes 0. 0 equals 2v1 v2 cos theta 1 plus theta 2. So 2v1 v2, when we take it to the left hand side, that again goes as 0. So therefore cos of theta 1 plus theta 2 is equal to 0, which is equal to cos 90. So therefore theta 1 plus theta 2 is equal to 90 degrees. So basically both the angles are complementary in this case. So theta 1 and theta 2 are complementary angles. So this is the correct answer to this question, and if you look at our following options, you can see that option B, 90 degrees, is the correct option. So what we did was we took conservation of momentum in the perpendicular directions. That means we took conservation of momentum in the horizontal component of the velocities and the vertical component of the velocities. And after that, we took the conservation of kinetic energy for an elastic collision. And then we then squared and added the two equations we got earlier, and then we applied certain formulae here and there, and using that we got theta 1 plus theta 2 as equal to 90 degrees. So the sum of the angles theta 1 and theta 2 is 90 degrees. That is option B. Next question. A particle of mass m executes a simple harmonic motion with amplitude a and frequency mu. The average kinetic energy during its motion from the position of equilibrium to the end is. So we need to find average kinetic energy in this case. So first thing to note is that we are undergoing simple harmonic motion. So in an SHM, the displacement in terms of time can be represented as a cos omega t plus phi, where a is the amplitude given, omega is the angular frequency, and phi stands for phase difference. Now, in this condition, we will consider phi as equal to 0. So then we get xt as equal to a cos omega t. So far, so good. Now we can find the velocity with respect to time. So that is basically the differential of the displacement with time. So a times d by dt of cos omega t. So we get minus a times omega times sine omega t as the velocity during simple harmonic motion. So now that we've got the velocity, we will apply the formula for kinetic energy. Kinetic energy Ke is given as half mv squared. So that will be half times m times a squared omega squared sine squared omega t. So it's basically minus, but then when a negative value is squared, it becomes a positive value. So now we have the expression for kinetic energy. Now what we're going to do is we're going to take average kinetic energy. So average kinetic energy is represented with the angular brackets. So open angular bracket and then half m a squared omega squared sine squared omega t. Now since all the others are not based with respect to time, so therefore they are taken out. So half ma squared omega squared is taken outside, and inside you would have sine squared omega t. Now the value of this operation is equal to 1 by 2, so therefore you will get half times half times ma squared omega squared. Now omega is angular frequency. It's represented as 2 pi times nu, which is the linear frequency. So therefore you will have 1 by 4 times ma squared 2 pi nu the whole squared. So you will get kinetic energy average as equal to 1 by 4 times mass times a squared times 4 times pi squared times nu squared. So 4 gets cancelled. So therefore you have pi squared ma squared and then nu squared. So the average kinetic energy is represented as pi squared ma squared nu squared for this particle in simple harmonic motion. So therefore, among the following options, option B is the correct answer. So we just found out we just applied the formula for displacement using simple harmonic motion. Then we found out the velocity, applied the velocity in kinetic energy. Then we used the operator for average kinetic energy. And then we applied some formulae with respect to frequency and and then we got the final answer, pi squared ma squared nu squared. This is the final question of this episode. An elastic string of unstretched length L and force constant K is stretched by a small length X. It's further stretched by another small length Y. Find the work done in the second stretching. So we have an elastic string and it's stretched. So elastic force on the string is a conservative force. So that is the first thing you need to keep in mind. So since this is a conservative force, the work done is equal to the negative of potential energy. So negative of the change in potential energy, so that is minus of U final minus U initial, which is equal to U initial minus U final. So the work done here is equal to the change in potential energy. This is the work energy theorem. So using the work energy theorem, we got the work done as equal to the initial potential energy minus the final potential energy. Now, potential energy in a string is represented as half times K, that is the spring constant, times the length stretched. So in the first case, the string is stretched by a small length X. So W here is equal to half K times the length squared, which in this case is X squared. Then in the second case, it is further stretched by a small length Y, so therefore there's already an initial strain, but then you you act on that strain. So therefore, the length that is stretched here is x plus y the whole square. So therefore, half k is taken common. You get x squared minus of x plus y the whole square. That is x squared plus y squared plus 2xy in a bracket. So the work done here is half k times x squared, and then we multiply the whole expression by minus. So x squared minus y squared minus 2xy. So x squared and x squared become 0. So you have half k times minus y squared minus 2xy. Now remember, all of this is under a minus. I mean, no, it's not under a minus. That part comes later. So half k times minus y squared minus 2xy. So here again, y is common. So half ky times minus 2x minus y is the work done by the string. So work done by the elastic string is half k times minus 2x minus y. So this is the work done by the string. We need to find out the actual quantity that we need to find out is the external work done. So the external work done in order to stretch the string has to be the negative of the work done by the string. So therefore, that is equal to minus half ky times minus 2x minus y. So when you take a minus common out of here, you get half ky times 2x plus y as the work done externally. So therefore, the work done in order to stretch the string to a length of x plus y externally is given as half ky times 2x plus y. So therefore, among the given options, option B is the correct option. We used the work energy theorem, and then we found out the work that the string does, and then in order to find the external work, we just multiply that with a minus sign. So therefore, option B is half ky times 2x plus y. That concludes this episode of BITSAT Practice. We hope you found this episode interesting. For watching more of our useful and interesting content, don't forget to subscribe to our channel, that is Brain Blitz Audios. If you like the video, don't forget to hit the like button. And in order to get more of our useful and interesting content, don't forget to hit the notifications button in the description down below. We also have added the link for the playlist, and that is BITSAT Practice, in the description down below. So if you want to access more of our useful videos regarding BITSAT, then you can hit that link in the description down below. So until the next webisode, take care, stay safe, bye-bye for now.